Hello, this is Mr. Hopkins Maths. Today we're going to be looking at hypothesis testing. This is the first part of our hypothesis testing series of videos, and today we're just going to be looking at a general introduction, what hypothesis testing is, and some of the key terms around that. Remember to like this video if it's useful for you, and subscribe and hit that bell icon so you know when you get the next part of this coming up. So, if we consider the following situation, a coin is flipped 10 times and the outcome is recorded each time. Now we are interested in how many tails appear. So my question is, what would you expect to happen? Well, knowing a coin, you would expect 5 heads and 5 tails if it's flipped 5 times. And that would be the theoretical expectation there. This is because the probability of heads or tails is about 0.5. And you would probably expect some variation around that value, maybe 4 tails or 6 tails or something like that. And if you're really lucky, maybe 3 or 7. But can we tell if a coin is biased? How many heads or tails would lead you to think it is biased? So if we got 8 tails appearing after 10, or 9 tails, or 10 tails, would that be biased? Well, this is what hypothesis testing aims to look at. So if we model this situation using a binomial distribution, we are going to let the random variable x be the number of tails that occur when a coin is flipped. And we can model this using the distribution x is binomially distributed, 10 trials, and a probability of 0.5. Now what I'm going to do is we're going to actually draw a table of probabilities on this. So if we look at this table of probabilities here, we can see that this is the probability of getting no tails. Here is the probability of getting 5 tails. And right down at the very bottom, we've got the probability of 10 tails. Now, because this is a probability of a half, so the probability of success is 0.5, and the probability of failure is the same, we get a very nice symmetrical distribution. So you can see that the values are increasing up to 5, and then they're decreasing. So from 10, they increase the same way. So it's like a mirror image kind of around this point here of your values. Let's have a look at this graphically. So this is my values here. So we've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Those are the number of tails. So and this is my probability of that actually happening. So as we can see here, 5 is the most common thing to happen. It's got just under a 0.25 probability. In fact, the actual value here, we've got 0.246. So to 2 decimal places, it's a quarter probability. And if you consider 4 heads and 6 heads, you can see that we've got around about 0.65 overall chance, cumulative chance of getting those 3 things. And even 8 has still got just under a 5% chance. Again, if you look back at our values, we can see that 8 is about a 4.4% chance there. But 9 and 10 have a very small chance of happening, as do 0 and 1. So if you're getting no tails or maybe 1 tail, and then at the other end if you're getting 9 tails or 10 tails, either you're just very lucky or your coin might be slightly biased in there. So we can use hypothesis testing to decide if our coin is going to be biased or not. Now, a hypothesis is a statement we make about the value of a population parameter that we want to test. And we do this by collecting evidence in the form of a sample. So in our case, it's actually going to be flipping the coin. Now, a null hypothesis, we would write this as h with a subscript 0 is our default position. Now, you would find people saying HO, H0, H nothing. I tend to go for HO, that's what I was taught, and I know that a lot of other people teach with HO as well. The alternative hypothesis is written as H with a subscript 1, and that's just H1. And so HO is our default position. This is what we would say if the coin isn't biased. So in this case, nothing has changed. The coin does exactly what we expect it to do until it's proven otherwise. H1, our alternative hypothesis, is that our population parameter has changed in some way. So we've got our coin possibly being biased at this point. So it is different to what we'd expect the default position to be. Now this could be validating a claim. For example, a company might claim one thing and then researchers test that claim and they either find the claim is validated, in which case the null hypothesis is proven, or they find that the claim is invalid from the company, in which case we go to an alternative hypothesis and we reject the null hypothesis. And we use words like reject the null hypothesis in favour of the alternative hypothesis. Now, what does this mean in the context of our example that we were looking at, which was flipping a coin 10 times and getting the number of tails? So our hypothesis, we want to know if our coin is biased. So that's our hypothesis. This is a statement about the probability of getting tails when the coin is flipped. The null hypothesis, this is our default position, is that the coin is going to be fair. The probability of getting a tails is 0.5. And then the alternative hypothesis is that our coin is biased towards tails. The probability of getting tails is more than the default, so the probability is greater than 0.5. So this would be biased towards tails. If it was less than 0.5, then it would be biased towards heads. But generally we would tend to set our hypothesis based around the actual value that we're looking to see if it's biased towards, perhaps. So let's have a look at a couple of key terms before we go any further. Test statistic. This is X. Okay, so this is our capital X and is actually what we have observed. In our case, in our context, this would be the number of tails observed when the coin is flipped 10 times. So we write this as X is distributed binomially 10, P. Now there's a reason when we're investigating hypothesis testing that we don't write P down, because the P that we're actually using is detailed within our null and alternative hypothesis. Until we start making observations, the value of P is actually going to be unknown. Level of significance. This is the maximum probability where we reject the null hypothesis. We often use something like 5% to 1%. Now, if we chose a 5% significance level, then what we're saying is that anything which falls below that significance level is unusual and unlikely to happen. And what we would say is that if an event has a probability greater than our level of significance, that's not unusual. That's probably within the realms of reasoning. That's going to be a perfectly fine event that could happen. So if the probability of our event, or unusual event that we're testing perhaps, was less than our significance level, then we would reject our null hypothesis in favour of the alternative. So for example, the chance of getting 10 tails is less than 5%. So if that's what we got, then we might consider rejecting the null hypothesis in favour of the alternative. That doesn't confirm that our coin is biased, but it implies that our coin could be biased. So we would normally say something like, there's sufficient evidence to suggest the coin is biased. Because if you have 10 flips and you get tails every time, the chance of that actually happening is very minimal. So testing at a 5% significance level would show that it's probably unlikely to happen. You might then go on to test it at a 1% significance level or something beyond that as well. So to summarise, we have a hypothesis. We wish to check if it's true or not. So our hypothesis in our case is our coin is biased towards tails. We collect a sample by flipping our coin. This gives us our test statistic. If that number of tails or more extreme, and I'll explain it in a moment, is unlikely to have emerged by chance, we reject our default position, which is called the null hypothesis, in favour of alternative hypothesis, and then we may have decided the coin is biased. Now, when we're testing, we test our value or more extreme. And this is quite an important concept. So if I wanted to say, is getting 8 tails biased, I would test the cumulative probability of getting 8, 9, or 10. So you test that or more extreme. Okay. And as we go forward through the videos, that's going to become much more apparent why we're looking at things like that as well. But as an introduction, we test that or more extreme. So let's have a look at an example. Alice wants to see whether a coin is fair or biased towards heads. She flips the coin 12 times and counts the number of times X it lands showing heads. So we're going to let P be the probability of a coin landing on heads. Then X is distributed binomially with 12 trials and some unknown P. What do? Well, let's define the null hypothesis. Well, null hypothesis we define as HO colon probability equals 0.5. And then our alternative hypothesis is she wants to know if it's biased towards heads. So if P is the probability of it landing on heads, if it's biased towards heads, then my alternative hypothesis is just simply going to be, so there's H1, my alternative hypothesis, put a colon in, P, lowercase p, is going to be greater than 0.5. And that way, if it's biased towards heads, then the increased probability will be towards heads, so it'll be greater than. Now, this is an example of a one-tailed test. We're only interested in one side of the probability. So in this case, we're saying that the probability has got to be greater than 0.5. There are examples of two-tailed tests. So in this one, example 2, Alice wants to see whether a coin is fair or biased. She flips the coin 12 times and counts the number of times X it lands showing heads. Let P be the probability of a coin landing on heads. Now, here is different if a coin is fair or biased. That's a very different thing. It's not saying it's biased towards heads, it's not saying it's biased towards tails. So let's define our null hypothesis. So HO, and I do my colon, my lowercase p, the default position is that the coin is fair, so it has a probability of landing on heads of 0.5. The alternative hypothesis, and this is why it's considered a two-tailed test, so is that P does not equal 0.5. Now, the reason for this is if you look at this, if P is greater than 0.5, it's biased to heads. And if P is less than 0.5, it's biased towards tails. Now, that's important there. We're looking at two different sides of this in this case. So this is what's called a two-tailed test. Why can we look at both? Well, it doesn't, in the question it says, is it biased? This coin could be biased towards heads, in which case the probability of it landing on heads will be greater than 0.5. If it is biased towards tails, the probability of it landing on heads will have to be less than that half value. So we take that into account by writing P does not equal 0.5, and that essentially covers both of these situations. So let's have a look at a more in-depth example. So an election candidate believes he has the support of 55% of the local constituents. Now, a local journalist wants to test at the 5% significance level whether the candidate is overestimating his support. The journalist asks 30 people whether they support the candidate or not, and 8 people say they do. Now, there are 3 parts to this question. A, write down a suitable test statistic, write down 2 suitable hypotheses, and explain under which the null hypothesis would be rejected. So let's look at the first one. Write down a suitable test statistic. So a suitable test statistic is simply the number of people who say they support a candidate. So for a hypothesis test involving binomial distribution, and you can do a hypothesis test involving normal distribution, but we're looking at it from a binomial point of view, the test statistic is always the count of successes. Okay? So in our case, the number of people who say they support a candidate is the success for this election candidate. Write down 2 suitable hypotheses. So the default position is that the election candidate is correct. So that his probability equals 0.55. Now, the journalist here says that they're overestimating. So they ask 30 people. So what they're saying is that if he's overestimating his support, the journalist that's investigating is interested in a support of less than 0.55. So the alternative hypothesis, H1, is that the probability is less than 0.55. And then if we look at the final part of the question, which says explain the condition under which the null hypothesis would be rejected. Our null hypothesis would be rejected if, and this is very important, the probability, and remember it all comes down to probability, so the probability of 8 or fewer, and remember we're dealing with 8 or fewer because the candidate has potentially overestimated his support, so we want 8 or fewer people. So the probability of 8 or fewer people supporting this candidate is less than 5% given that P equals 0.55. So that's the situation that we would reject our null hypothesis if the probability of 8 or fewer people supporting this candidate is less than 5% given P equals 0.55. So that's this video introducing hypothesis testing. We've looked at it in realms of binomial distribution as an introduction. If this video has been useful to you, remember to hit the like button and subscribe so you know when the next part of the hypothesis testing is coming out. Coming up in the next few videos, we're going to be looking at critical values. We're going to be looking at how to complete a full hypothesis test as a one-tailed test, and also how to complete a two-tailed hypothesis test, both of which we've briefly touched on in this video. Until next time, goodbye for me.